Hello, this is Ayush Vikram here, and today I'm going to present my presentation. Um, my project was on a naive Bayes sentiment classifier. So my problem statement was I wanted to develop a classifier to predict the sentiment of reviews, right? You give reviews based on a service or product that you use and your experience with that product based on the words that are used in the review. So based on the words used in the review, can we predict the sentiment of the review, whether it's a positive or negative review? And I wanted to develop a classifier using the naive Bayes kind of algorithm. So again, how are we going to develop this classifier? So as I mentioned before, I wanted to use a naive Bayes approach. So the naive Bayes is quite simple. We want to classify this posterior probability, a probability of C given X, where C is your classifications, your class given X. And likelihood is, so the posterior probability is equivalent to the likelihood probability times the prior class probability and divided by the probability of X, right? Your predictor prior probability. And this is just based on Bayes' theorem of calculating conditional probabilities. So what is P of C given X? The posterior probability. Well, C is your class. So in our case, there's only two classes or classifications. There's a negative and positive, right? Negative reviews or positive reviews. So probability of C given X would be something like probability of negative review given X and probability of positive review given X. Now, what is X? X, as you might have guessed, is quite simply just the words that are in the review that we want to classify. So if the review is, I had a great time, then the words or X is are I had a great time, right? Right? And to calculate the posterior probabilities, we have to calculate the likelihood probabilities, and we do this we calculate the likelihood probabilities in the training step, and the posterior probabilities are obviously calculated in the test step when reviews are classified. But the likelihood probabilities are calculated in the training step, and they are, as you can see, the probability of X given C. And as I mentioned already, the X are just the words that make up the review that we want to classify. So probability of X given C is probability of the words given either the positive or the negative class. And um, thanks to the assumption of conditional independence, we assume using the bag of words model that a review just consists of a bag of words, right? A bunch of words that are sitting almost independently of each other, and their relative position to one another doesn't matter. So thanks to this assumption of conditional independence, as you can see in the bottom of the image, the probability of C given X, right? That's the likelihood probabilities, which are these conditional probabilities of X given C, are broken up into a product of these individual likelihood probabilities, right? X1 given C times X2 given C, all the way up to Xn given C. What is X1, X2, X3, X4, all the way up to Xn? These are the words that are in the review that we want to classify. So probability of X1 given C is basically the frequency of the first word, whatever the first word of the review you want to classify is. Let's say it's this. It's the frequency of this in all reviews of class positive, right? From our training step, we've calculated this, right? Or negative, right? Maybe we want to we do it for positive and negative both. So essentially, to calculate, right? So that's how the likelihood probabilities are calculated. They are essentially a product of these individual likelihood probabilities, where it's each where the probabilities are the probability of each word given the classes, right? Either positive or negative. So to classify using this naive Bayes model, we have to note that, right, our we have our posterior probabilities that we want to calculate, right, which is quite simply the likelihood probabilities times the prior probability. And we note that to maximize the posterior probability, we can kind of forget the denominator, right? We just have to maximize the numerator. So when we're actually building these classifiers, we just use the numerator, and right, and all we do is we take the maximum, right? So since we have two classes, positive and negative in this case, we're going to have two posterior probabilities, right? We calculate the likelihood probability for each word in our review for the negative and the positive class, multiply by the priors of the negative and the positive class, and we get the two posterior probabilities, and we simply choose whichever one is greater, right? These are the posterior likelihood probabilities times prior, likelihood times prior. These are the two posterior probabilities. We choose the maximum of them in the test step. And whichever one is the maximum, that is what we classify that review as. So if one review has a greater positive posterior probability, that review will be classified as positive, for example. And you might be asking, how are these prior probabilities, right? This probability of class equals positive, probability of class equals negative, or here where you have this P of CK, P of CK, these are the prior probabilities. How are they calculated? Well, they are basically estimated. You can estimate them based on your prior knowledge. You can estimate them using like maximum likelihood estimation, right? So those are kind of based on your prior knowledge, or kind of based on a sampling, because it's kind of hard to estimate the probability that a review will be positive, right? So you need some kind of calculations or experience to get that value. So the likelihood probabilities, as I mentioned, which are these right here, these probability of x1 given ck times x2 given ck times x3 given ck, right? That product of um, the probability of a word given a class, word given positive, word given negative, right? Those likelihood probabilities, let's talk about what they are. They're calculated in the training step, and they're defined as the count or frequency of a word. So a word can be a unigram, a single word, or it can be a bigram, right? Or whatever, a trigram even, depending on your model, plus this k. K is a Laplace smoothing constant. Um, so Laplace smoothing is done because, let's say a word does not show up in your training set, but it does show up in one of the reviews of the test set. So we don't want to assign that a likelihood probability of 0, because that's not true, right? I mean, a word cannot, because your test training data set is limited. It's not the entire world, right? So a word might easily exist in the test set that doesn't exist in the training data set. So we want to give it a small probability, but not a 0 probability, right? So we add this k to it, some constant that's up to you to decide, and divided by this n plus again this k constant times the magnitude of words. So what does this really mean? So count of word is again the frequency of the word. K is again the Laplace smoothing constant. I just used 1. N is the number of words in reviews of that class. So if we're trying to calculate likelihood probabilities for, positive, right? The word given class right here, these are likelihood probabilities. Let's say our class is positive, then the number of words in reviews of class positive. Same thing with negative, right? And this magnitude of x, or magnitude of words, is the number of unique words in reviews of both classes. But since there are only two classes, we have all reviews in the training set. It's the number of unique words in all of the reviews of the training set, right? So quite simply, a naive Bayes classifier kind of operates like this. The posterior probabilities are calculated by the prior times the likelihood, right, divided by this evidence, the denominator. But we disregard the denominator when creating naive Bayes classifiers, as maximizing the numerator, which maximizes the posterior probabilities, and we just need to take the maximum of the two posterior probabilities to decide which class the review belongs in. Um, so let's talk about let's talk about again, this is the definition of likelihood probabilities. Why naive Bayes, right? So naive Bayes is a simple way of training. It has a simple training, especially when we're dealing with labeled data. So when we have labeled data and we're working in a supervised learning kind of method, it's very easy to train a naive Bayes classifier. It's simple compared to other classifiers, which gives it a major advantage, and which makes it attractive to people studying classification problems in companies and industries involved. in classification problems. Another reason is naive Bayes is simple to train, but despite that simplicity, it can be quite accurate. It can be very highly accurate, depending on depending on the circumstances. And along with the high accuracy, it is actually very efficient compared to classifier algorithms. So I think it's almost linear time, and not a lot of classifiers are like that. So it's quite efficient as well. Um, so let's talk about how specifically I implemented the project, right, with the naive Bayes. So what did I do? I trained two classifiers. The first one was a unigram classifier. That means that I considered individual words. Uni means one, right? So when I was like, for example, that means when I'm calculating likelihood probabilities, I do the count of one word, right? And this word is also the number of unique one word, unique singular words. Uh, for example, and same thing with this n. Um, so I created a unigram classifier, and then I also trained a bigram classifier. So a bigram just means that instead of this being a word, a singular word, and this being defined in terms of singular words, now we're defining them in terms of bigrams, which are pairs of consecutive words from the reviews. So the review does not consist of a bag of singular words; it consists of a bag of bigrams, essentially. But it's the same process. Just, you're essentially replacing the singular words with the bigrams, essentially, right? The frequencies and the accounts and everything like that, with of the unigrams with bigrams. So the reason I kind of did that, my hypothesis was that I think maybe a bigram classifier would be more accurate because it's picking up the certain groups of two words that show up, and I think there might be groups of two words that tend to show up in reviews of similar sentiment, right? And I think two groups of two words. My hypothesis was that maybe it's more accurate than just using singular words, because like singular words can be influenced by kind of these like random outlier words, and maybe you want to say something is not good, but you pick up the word good from that in the singular kind of naive Bayes, and then since you're not considering the position, right? You pick up the good, and you say, oh, like that was a good experience. Whereas in a bigram, you see not good and the not good are going together, so so at least you have a chance of understanding that review is referring is referring to a not good, pleasant experience, right? So that was my kind of hypothesis and prior kind of guess as to why I chose to also do a bigram classifier. So right, the in both cases, a list of kind of predicted labels is returned, classified labels, um, and accuracy was mentioned. And so let's go on to the data, right? So the data was quite simple in a table format originally from Kaggle. 3 columns. The first column was an ID. So that went all the way from 1 to, I had more than almost around 107,000 rows, right? And each row consisted of 3 columns. As I said, the ID, uh, which went from 1 to like 107,000. The review was the actual review in words. So each review was a string. So that could be like, oh, I had a great experience, I learned a lot, blah, blah, blah. Or whatever, right? And the score was a numerical score affixed to the. It was a score, right? It was a numerical score, so it was not verbal like the review. It was from 1 to 5, and the score helped to serve as the label, right? But I was classifying into negative and positive reviews, so I needed to take that score and turn it into a label. So what I did was a 4 or a 5 corresponded to a positive review, and anything lower was a negative review. So that's how the data was organized, and I turned it into a pandas data frame. And if you look, and in as we in my kind of project, obviously I had to process it and clean it and things like that. So the cleaning was removing the punctuation and replacing it with spaces, and then making everything lowercase. And I put the array, I changed the format of the reviews. So I wanted the format to be a list of lists where each individual list is the words present in one review. So like, let's say my array, my 2D array, let's my 2D array of reviews. So reviews 0 would be the list that consists of the words of the first review. Review 00 would be the first word of the first review. So I wanted it in that 2D structure. So I split the reviews in that structure for both the training and test sets. Um, and I also created the labels, right? Greater than 3 was a positive, else 0 or a negative. And then came the training set. So we needed to calculate the training set. As I mentioned, we need to calculate the likelihood probabilities. So again, here is the training and the test implemented in my class, Naive Bayes class. This is the unigram. So I have counters that hold the frequencies of each unigram. I have length. This is just a running sum. This keeps track of how many words or unigrams there are in like positive reviews total and negative reviews as well. And this is just a set of all words in both classes, so it just holds the unique words in both classes. So this is for so we just iterate over each of the training labels, and if it's a 1, the review is a positive, so we update our counter with the frequency of the words in that review, and same thing with the length of the number of the length or the number of words of in the positive reviews. Same thing with negative, and we update the total set of all words as well. And then we calculate here. We are calculating the likelihood probabilities, right, which are just the frequency along with Laplace smoothing. And this is just following exactly the formula I mentioned previously in the video, my introduction. And then the classification or the test stage comes, and now we are just classifying, we are calculating the posterior probabilities, right? And then we do that by multiplying the likelihood probabilities, as you remember, with the prior probability. But what I did was instead of multiplying probabilities, which are small numbers, right? And if you keep multiplying small numbers, you get closer to 0. I used log. So that logarithm changes the multiplication into addition thanks to logarithm properties, and it avoids underflow as well. So that I applied logarithm, and then quite simply as I stated, we do a max operation. So we classify the review as the class with the maximum posterior probability, and that's it. And then I had a function to measure the accuracy as well. So quite interestingly, I did that for both the unigram, and then I also did a bigram class as well. So the bigram class is similar. I have just generate bigrams function, but the rest was quite basically the same for bigrams and unigrams, right? Just change the unigrams into bigrams. So now I'm not tracking the frequency of a unigram, I'm tracking the frequency of a bigram. And now I'm tracking the number of bigrams in each class and the total set of bigrams and not unigrams. And doing the same thing, calculating the likelihood probabilities in the training stage for each bigram, right? Not like individual words, but it's the same idea. Um, and here we calculate the posterior probabilities of each bigram in negative or positive class, and we apply logarithms again to reduce underflow, the chances of underflow, and we have an accuracy function here as well. And as I mentioned in my earlier, in the beginning, prior probabilities are kind of like your own estimation or your own kind of prior belief or whatever, right? Or however you want to calculate it. Perhaps you have other studies done. So in this case, I simply calculated it by going through the data set, the training data set actually, um, and seeing what proportion of the training data set were positive. So that's how I got the positive prior probability, and the negative prior probability is just 1 minus that probability, right? because a review is either positive or negative. So, and then I have this again, the function to calculate the accuracy based on the proportion of correctly classified reviews. So let's talk about the results. Um, the results were I'm quite pleased with the results. So let's talk about the unigram performance. 91.6033% of test reviews in the test set were correctly classified by the model, the unigram naive Bayes model, and 8.396% only were incorrectly classified. The bigrams had a higher performance. The bigrams correctly classified 91.9042% of test reviews in the test set, and they incorrectly classified only 8.0958%. So I was very pleased with this. 91% is a high accuracy, especially when to kind of give you an idea, there were 53,000 tokens in each the training and the test set, right? Because the beginning I mentioned that the total number of rows were 107,000. So I was quite pleased with this outcome, and I also investigated the errors that arose, right? So I remember among the kind of the 8%, let's say, of reviews that were incorrectly classified, among the errors, and for the unigram, 41% were false positives and 58% were false negatives, and 48% were false positives in the bigram, and 51% were false negatives in the bigram. So it's interesting. The bigram had a more even distribution between false positives and false negatives. And there are certain industries and certain applications when you might want to encourage, when you might want to minimize or maximize false positives at the expense of the other, or false negatives, right? And vice versa. For example, let's say you want to, you don't want false negatives, right? Like false negatives are when something is true in actuality, but you classify it as a negative, right? Let's say you don't want false positives in your classification problem because, like, if something gets missed, it's a dangerous situation, right? Let's say it's that kind of scenario where a miss is potentially dangerous. Then you want to minimize false negatives. Right. So that's one example where you might want to minimize one of the false positives or false negatives. But so let's say you want to minimize, if you ever have a scenario when you want to minimize false positives, right, it's better to let things go in your scenario than unnecessarily calling things out and creating alerts or whatever. Then maybe you want to go with the unigram model, which has a lower false positive rate. If you want something that's kind of even and has a kind of almost equal chance, equal distribution of errors, you might want to go with the bigram model. So it depends on the application, right? So that's basically it. And again, I wanted to state that I think to answer the kind of guiding question at the beginning, I think the naive Bayes model worked splendidly well in classifying, in providing a sentiment classifier for a review based on the words in the review. It worked wonderfully with kind of 91% accuracy with the unigram and bigram. Something that I think can be further done to explore this avenue is creating a mixed model. So instead of just using a unigram or a bigram model, let's combine the two in a mixed model. Right, let's combine the two, excuse me, in a mixed model where the posterior probability will be a combination or sum, right? Some sort of sum of the two posterior probabilities for the unigram and bigram model. So that's one thing I think would be a good future exploration and good thing to explore. Another thing would be incorporating higher degrees of n-grams, maybe trigrams, 4 grams, and maybe combining them into some sort of mixed model as well with the bigrams and unigrams. Um, and yeah, I think this was a good, promising start. And I think because of the fact that naive Bayes makes the kind of assumption, right, like the assumptions of conditional dependence and bag of words assumptions as well, it's a very simple algorithm to train, and that makes it a worthwhile classifying tool. And I think this proves that, even with a kind of a simple home project, you can make some powerful, you can gain some powerful tools in solving classification problems using a naive Bayes model. And I think the results prove that it is an effective model, and it's effective training, and it's kind of quick training, and its kind of ease of usage makes Naive Bayes a very, very powerful tool. I think that's the point of this project and the large takeaway. So thank you.